So we covered a lot of ground actually last time. Sections 1 through 5, we talked about discovery of the atom, parts of the atom, electrons, nuclei, Bohr's theory, X-rays. You know, the characteristic X-rays that each different material gives, kind of that kind of stuff, and the applications of atomic excitations and de-excitations. And then now we're kind of getting to the point where we need to start talking about what are the quantizations of matter? What are we talking about when we talk about quantum numbers and things like this? And if you remember, in the previous chapter, actually in the previous two chapters, we started talking about light becoming a particle and particle having a wave nature. So there's this particle-wave duality thing going on, where waves now can behave like packages of energy, and where particles can have a matter wave that's associated with them. Well, in the atom, this actually connects to a lot of things that are quantized in the atom. For example, an electron has a particular wavelength, and that particular wavelength, if you stretch it out around the atom, if not stretch it out, but if you connect it around the atom, it fits around at about where we would think the radius of the orbit of an electron would be if the electron was orbiting. So it kind of correlates to that. And it also creates some shapes around the atom that in 3 dimensions start to look like where these electrons are actually discovered or actually found when we do experiments. And so we start to see that this wave, this matter wave or this probability wave is physically manifest in the atom's behavior. And it's physically manifest in the atom's quantum behavior because these waves cannot be put together in such a way that they don't connect cleanly. So if you were trying to wrap a wave around an atom and it didn't wrap around enough times to connect, like you left with a broken spot in your wave here, that would mean that this particular arrangement of the electrons just wouldn't happen. And it doesn't happen. It only happens when you get this nice clean wave that connects all the way around and reconnects to itself. So this actually has something to do with the quantization. You have to have the right kind of wave to fit.
So the messed up path is the path the electron takes around the
No, it doesn't take any path. This wave is they're just superimposing this wave over the Bohr orbit. So this is the orbit that Bohr thought the electron took, this circle. And this is the matter wave that comes from quantum mechanics and from Einstein's work and other people's work. This is the matter wave kind of superimposed on top of it. And because the matter wave superimposed on top of it kind of averages out to look kind of like this circle, if you averaged it, it kind of would be at the same distance as that circle. That is the correlation. The correlation is that Bohr's energy corresponds to this wave, this matter wave. But if you have a particular orbit that you're trying to achieve, and you try to superimpose the orbit on it, and it doesn't average out, it ends up not fitting all the way around, then that particular orbit will never be achieved by an electron. You'll never see an electron in that orbit, is what they discovered. So that's where the quantization comes in. It's just a correlation. It's not an actual mapping of what the electrons do. And so this comes out in these quantum numbers, like Bohr said, you know, we have this n equals 1 state, this n equals 2 state, this n equals 3 state. And that comes out also in the wavelengths of the electrons that are allowed. So the wavelengths have matter waves associated with them, and those matter waves have wavelengths, and they're associated with these energies that Bohr put in there, and those energies are associated with a radius, with an orbital radius, but it's not really a radius of an orbit. It's actually just kind of an approximate position out there in 3-dimensional space where this electron might be found, according to the statistics involved. And if you solve this equation that includes the quantization and Bohr's theory in there, you solve this here, you find out that there's a lot more quantization involved. For example, this right here starts to look like angular momentum because it's something over velocity. We've seen this before. And so if you solve that, the angular momentum would be the m times the v times the r if you divide by the r on both sides. And this is angular velocity, m times v times r. So m times v being the radial or the just linear velocity, r included in there gives it an angular velocity. So this is an angular velocity. So if we solve that for this m times v times r, then we get that the angular momentum inside of an atom, or the angular momentum of an electron inside of an atom, is equal to nh over 2 pi. That means that the angular momentum is quantized just like the energies are quantized. Which of course seems ridiculous to us. You think, how can angular momentum be something that only can be this value, or this value, or this value? Because angular momentum is just determined by your radius and your mass and your velocity. So if you change your mass or your velocity or your radius, you can change it to any value you want. But according to this, you can't. According to this, an electron in a particular atom only can achieve certain angular momentums at certain energy levels. And so not only is the energy of the electron in an atom quantized, but the angular momentum of the electron in the atom is quantized. And then, as they were studying this more and more, they started to discover that not only does the electron have angular momentum when it's in the atom, but the electron has angular momentum all by itself. An electron has angular momentum on its own. How do you know if something has angular momentum? Well, you can do a couple of different things. One of the things you do, since an electron is a charge, if you put an electron in a magnetic field, so for example, you have an atom with all these electrons in it, and you put it in a magnetic field, anything with angular momentum is going to be affected because if it has angular momentum, it's like it's a moving charge, and moving charges are affected in the magnetic field. And so what happens if you put an atom in an electric field? What happens to the angular momentum part of those electrons? It actually moves the energy levels. So the energy levels change, and really what happens is they shift. So they all shift a certain amount. And that shift was the evidence that there was angular momentum, and then they discovered that the shift was always the same amount every time for each level. Each level had a shift that was related to this equation. It was related to the mass of the electron, the Bohr radius of the energy level, and the Bohr velocity of the energy, but it wasn't really any of those things. It was actually related to this. It was actually related to the principal quantum number of the energy level the electron was in, and then h over 2 pi. It was actually just the principal quantum number that changed it. So if you were in n equals 3 level, you had a different shift than you had in the n equals 2 level. But it was always a shift that was proportional to h over 2 pi. So if you're in the 3rd level, you had 3 times as much shift. If you're in the 4th level, you had 4 times as much shift as the 1st level, and so on. So they discovered this was the case, and then they also discovered that
So whenever the electrons are moving previous to that angular momentum.
what's that?
So whenever the electrons are moving free, like whenever they're jumping from one atom to another, they're also having.
Yeah, they discovered that even on their own, electrons have their own angular momentum that's different. And so they were discovering all kinds of things. Another thing they discovered is when they put atoms in a stronger magnetic field, it split the states up. So instead of just shifting the states, it actually split them. So if you had one state that would split into several states. And so this was also quite interesting. And what they discovered is that if you were in the n equals 1 state, it didn't split the states. It would just shift. But if you're in the n equals 2 state, then you would get some splitting going on. If you're in the n equals 3 state, you would get more splitting going on. And the higher you were up in the atom, the more splitting you would get going on. And so they started studying this and discovering the rules for it. And in these rules, what they discovered was what we're going to learn next, as they were putting together, as they were doing all these observations. So here's the splitting that I was just telling you about. In the n equals 1 state, or sorry, this is not n equals 1. This is just, they don't tell us what this is. But in any particular state, if you have no magnetic field, you don't get any splitting. But you get splitting as you get an electric field. If you have a really, really big electric field, you get even more. The splitting becomes even bigger, right?
This is how far the electron is from the nucleus.
So what you're seeing here, this is not how far the electron is. This is the energy that the electrons come out with. So when you have no electric field applied, all the electrons come out at this really close to this energy level. You have a little bit of electric field, and electrons start coming out at certain energy levels. They're all kind of close together, but there's only 3 distinct energy levels. And then as you apply more magnetic field, those split energy levels split further apart. And sometimes it'll split into 3, but sometimes it'll split 1 into 5, or 1 into 7 even. It always splits into an odd number, it turns out. But when it splits, but magnetic field is the thing that causes it to split. They call this the Zeeman effect, named after the guy who discovered it. Oh, excuse me. And the way that they first described this is they said, well, this is as if the electron is going around and around the atom. That is like angular momentum. And even though we know the charge isn't doing that, we know that that can't be the case, it still behaves as if it does that. And so we're going to still call it angular momentum. And they call this the angular momentum quantum number, or orbital angular momentum, they often call it, or the anyway. And they also call this space quantization, because the bigger the magnetic field, the bigger the split there is in the energy levels. So they get spaced out even more, you could think of it as. But then this part where the electrons have their own angular momentum, which is an intrinsic, they call it intrinsic spin here. They said, well, maybe that's due to the electron spinning. Well, even electron spinning can't happen, because they would decay and they would become less energetic, and then they would all collapse inwards towards something. So even that is not allowed for them to spin according to the laws that we know. But what they discovered is if you look really, really closely at individual electron lines in the spectrum, you will actually see 2 lines. And they said, wait a second, how is that the case? And what they discovered is that electrons have angular momentum, but their electron angular momentum can only exist in 2 states. There's only 2 kinds of angular momentum. It can't just be, so if the electron was spinning, it would either be spinning clockwise or counterclockwise at a particular speed, if it was actual spin angular momentum. And what this means is that electrons have a very interesting behavior about them. That is, it's like they're either heads or tails. They're like a coin. They're either spin one way or spin the other way. We call it spin up or spin down, because what happens if you put them in a magnetic field, if you have electrons, if you fire electrons through a magnetic field, half of them will go up and half of them will go down in the magnetic field because of this spin characteristic. So we call the ones that go up spin up, and the ones that go down spin down, just because it's easy to call them that. So electrons only come in one of these 2 varieties, spin up or spin down. And the really interesting thing is that we discovered is that in these valence shells on the periodic table, these valence shells always come in even numbers. There's always an even number of valence shells. So this first valence shell has an even number. It can have 2 in it. Hydrogen has 1 electron in its valence shell, but helium has 2, and it's filled up the valence shell. Going across the periodic table fills up the valence shell. So helium's is 2, and it only has 2 electrons, and one of them is spin up, and one of them is spin down. And it has to be that way. This is called the Pauli exclusion principle. If you have one spin up electron, and another electron wants to join it, it has to be a spin down. You cannot have 2 spin ups, you cannot have 2 spin downs. They only come in a spin up, spin down pair. That's how they couple together. That's how they pair up together. In this second valence row here on the periodic table, the second period, you have this shell here which has 2 in it, and then this that has 6 in it. And so this one actually fills first, and technically they often say, they just usually say this valence shell is 8. But anyway, what happens though is that this one will fill, and then this one will fill, and then this one will fill with electrons, all the way up until you're halfway done. So halfway would be here. And each one of these would have 1 electron in it that's either spin up or spin down. And then you would put another electron in each of those, you could think of those boxes that hold electrons, 2 electrons each. Once each one of those boxes has 1 electron in it, either spin up or spin down, then another electron is put in that is the opposite. So they always pair up as 1 spin up, 1 spin down. And here they show all kinds of representations of how these angular momentums and spin might be related to classical physics, of course. You know, the electron going around the nucleus accounts, is kind of like the angular momentum, and then a spinning electron might have something to do with this spin. But the really interesting thing is the spin is not actually, if the spin was spinning electron, it wouldn't be spinning in a vertical axis relative to its orbit if it wasn't in orbit. Because we discovered that the energy actually would correspond to a spin that is 54.7 degrees from the vertical, which is kind of interesting. So anyway, there's just a lot of interesting things that were learned as they studied this. So now we have another quantum number because the spin is only one thing or another thing. It's quantized. It can't be any old number. It is quantized it's either up or down. It's either one thing or the other. So we have one more quantum thing. And every one of these is given a value. There's an actual value that you can calculate. And for example, for the principal quantum number, you can only have principal quantum number 1, 2, 3, 4, and there's an equation that calculates the energy of those levels for the hydrogen atom, right? That's the Bohr energy of the levels. So that was the n squared times 13.6. 13.6 divided by n squared, sorry. It's right there actually. 13.6 divided by n squared is, in electron volts, is the energy levels. That's how you calculate the energy levels using those quantum numbers. And then it turns out for momentum, for the angular momentum, the quantum number is different. We use little l for the angular quantum number. And it actually starts at 0, because if n equals 1, if you're in the n equals 1 state, there is no angular momentum. So you have to start with L equals 0 so that you get no angular momentum at the first state. So the first angular momentum state is 0, and it goes 0, 1, 2, 3, all the way up to the highest n level that you have, -1. So you can have all those possible angular momentums if you have all these possible n's, right? And remember that as these atoms get bigger and bigger, you have more and more of these levels filled up with electrons. Essentially, each row in the element in the periodic table is an n number. It's a which corresponds to a principal quantum number.
Considered a layer of the.
Yeah, you could consider them as shells. But really, any atom can have those energy levels. So hydrogen can have an electron that's in an energy level that is normally associated with like tungsten in its ground state. You can force an electron in hydrogen to jump up to a state that's really high, that for tungsten is just normal, you know? So any of these atoms can have any of these states, okay? And so the angular, so these are things that we generally have to remember or know where to look up. So n is going to equal 1, 2, 3, and so on. And then L, for n equals 1, L will equal 0. For n equals 2, L can equal 0 or 1. For n equals 3, L would equal 0, 1, or 2, and so on. So it goes like that, essentially, depending on what you're, and it goes all the way up to n minus 1. Right? So
the number, the L,
so whatever, n is your principal quantum number. That's the thing that you use to calculate your energy level, the main energy level that you're in. That's the number that you use to calculate that. This is the number that you use to calculate the angular momentum of the electron in that energy level, whatever energy level you're in for n. So essentially for every electron in every atom, you're going to have an n, and you're going to have an L. And that will determine, the n will determine the energy level, the L will determine your angular momentum in that energy level. Okay? Then, the splitting of those levels, remember we talked about the splitting of those levels, is determined by this quantum number. The splitting is caused by a different aspect of the angular momentum, and we call this the z component of the angular momentum. So it's a component of the angular momentum that is perpendicular to the orbit, if it was in an orbit. So this one is called, the angular momentum, and the z component of the angular momentum is called L sub z, and it uses another quantum number, m sub L. Right? So m sub L, whatever L you're in, which is determined by whatever n you're in, whatever L you're in is going to determine what m sub L could be. M sub L can be whatever your L is, negative, and then the next number up from that, all the way up to 0, all the way up to positive. And you're like, what the heck are you talking about? I'll explain this in a second. We'll go through it again here in a second. And then, of course, there's one more quantum number. What's the last thing that can happen? What's the last thing that can affect the overall behavior of an electron? It's spin, right? So what do we have with an electron? We have an electron that's at a particular distance or energy level, right? So the distance or its energy level determines its behavior. How much angular momentum it has determines its behavior. That's the little l. The z component of the angular momentum determines its behavior, determines the splitting. That's the m sub L. And then whether the electron itself has its spin up or spin down. So that's the last quantum number, spin up or spin down, which is m sub s, which is here somewhere, right here. M sub s is our quantum number for that. So these are the 4 basic quantum numbers of atomic physics. Are these all the quantum numbers? Absolutely not. But these are many of them. This is a good representation of the quantum numbers in quantum physics. So what does this all mean? Let's go through and talk about what this all means. Let's see where's a good picture that we can use. So with each of these numbers, there's an equation that we use this number in to calculate something about the electron, okay? Or in essence, to something about the atom as well. If you calculate something about the electron in that atom, what you're really doing is calculating something about the atom. So let's talk about hydrogen or hydrogen-like atoms, hydrogen or things that are like hydrogen. When you say that things are like hydrogen, it means that it's an atom that is missing all of its electrons except one. So if you have tungsten that's like hydrogen or hydrogen-like, for tungsten, normally tungsten has 74 electrons in it. If you subtract 73 electrons from tungsten, then it's like hydrogen. It only has one electron, right? And then it becomes easy to do this math, and we can actually apply this math to tungsten. So if it's hydrogen or like hydrogen, then we use this number to calculate the main energy level, or the principal energy level of the electron. And we use this equation to do that. E sub n equals, let's see, it's 13.6 Z something.
So E of n is E of that level.
It's the energy level for the principal quantum number n. That's correct. And they don't show it here, but it's this. They show the basic here. Basic thing here. It's proportional to 1 over n squared. So we have an n squared down here, but it ends up being I think Z times 13.6 electron volts over n squared, where Z is the number of protons in the nucleus. And I think it's Z, but where is it? It's Bohr's theory. Ooh. Right here. Not quite here. Right here. Z squared. Z squared over n squared times.
So this here would be the energy and the electron and the whatever level.
Yeah. So if it's a hydrogen atom, you use 13.6. But if it's not, you just take E naught, which is the energy level at the lowest energy level, or the ground state. So E naught is the ground state energy, multiplied by Z squared divided by n squared.
So are all these E naughts already figured out for?
Yes, for these atoms, they are figured out. This is not something you're going to have to do a lot of calculating for. They'll tell you what it is. So, but this is the equation that uses this principal quantum number. If you have this number, if somebody comes along and says, then says I have an atom that's in, let's say that we have tungsten in the n equals 4 energy level. That's what they'll say. It's in the n equals 4, or the principal quantum number is 4. You know, they'll say it's in the 4th excited state or something like that. 4th excited state means it's in the 5th level actually. If it's in the 1st excited, like the ground state is n equals 1, the 1st excited state is n equals 2, 2nd excited state is n equals 3. But anyway, they'll either tell you what n equals, or they'll tell you what level it is. They'll tell you, it's in the 4th, it's in n equals 4 or whatever. Or they'll tell you it's in the 4th excited state, which would actually be n equals 5, because the 1st excited state is n equals 2. Right? So they'll tell you something like that tells you what n is. Once you know what n is, let's say that n equals 4. If n is equal to 4, then you know all of the possible quantum numbers that go with n equals 4. What possible quantum numbers of L go with n equals 4?
3, 2, 1, 0.
Yeah, so L can be 0, 1, 2, or 3 if n equals 4. What can m sub L possibly be? What possible states can you be in? Here.
-3.
You could be, now for each one of these L's, you're going to have a different possible state, aren't you?
Yeah.
So you have to kind of split it up. If you're in the L equals 0 state, of course, then m sub L is going to be 0. But if you're in the L equals 1 state, it could be -1, 0, or 1. If you're in the L equals 2 state, it could be -2, 0, or 2. So you'd have, for each one of these, you have a different possibilities for m sub L. And for each one of those, you have 2 different possibilities for m sub S. Either spin up or spin down, right? So, and we'll get to there in a second. So essentially, we use these numbers to determine what states we could possibly be in. But each one of these numbers, like I said, calculates something. So for this one, if we go back to where we were, which was quantum numbers and rules. So for the L quantum number, or the angular momentum quantum number, goodness, this is jumpy today. There we go. Okay. For the L, we can calculate the angular momentum, which is going to be this equation here. L equals L times L plus 1, little l times L plus 1, square root h over 2 pi. So, that's where the quantum number comes in, and h over 2 pi is here. So that will calculate the angular momentum for any particular L that your electron might be in. And then for m sub L, that calculates the L sub z. That calculates the z component, just one part of this angular momentum that is associated with that fine structure or that splitting of the energy levels. And this is how you calculate it here. M sub L, you use the M sub L quantum number and multiply by h over 2 pi, and that gives you that particular value of the momentum.
So you gotta put the M sub L in the square root thing.
Well, you put the L in the square root.
So do you gotta figure out every one? Like for 3, you have to figure out 2, 1, 0?
Just a minute, we'll get to that in a second. Right now, I'm just trying to lay this out for you, and then we'll show you how to calculate, okay? Because if we take a break right in here in the middle, we'll get a little confused. And then the last one, which is the spin, is also associated with a number. So we have m sub s is our, well, actually they're just calling, well, actually there are two. There is actually s and m sub s, because there's s and there's m sub s. So the spin is square root s times s plus 1. So this is kind of like calculating the angular momentum again, and h over 2 pi, but it turns out for electrons, s for electrons, when we do it, is always equal to, and they show this on page, whatever this page says in truth. S for electrons is 1/2, it turns out. So that makes it really easy. That's little s. Sorry, I did this one. Sorry. This is actually the calculation of this thing. So this is big S. This is little s. Little s equals 1/2 for electrons. And to calculate the actual spin, this would be spin angular momentum. Angular momentum from the spin. You use little s times s plus 1 square root h over 2 pi. So notice that the angular momentums here and here are the same calculation, just with a different quantum number. Then there is also the spin up, spin down. The spin up, spin down thing is this other one, where we use m sub s. And m sub s for electrons is always either -1/2 or +1/2. Same rule here and here, right? Except we don't have a 0 in there. There's spin up, spin down. And then the m sub s, which calculates the z component of the spin, which is the thing that causes the spin up, spin down situation. You use m sub s times h over 2 pi, very similar to this one. So essentially we have 5 things that we can calculate about our electron in the atom. And we have 5 different quantum numbers that are used in calculating. Now you ask the question, how do I calculate something for this? How do I do a problem like this? Okay, so that is a great question, because in any situation with any electron, any single electron inside of an atom is going to be in one of these states. What I mean is it's going to have one of these numbers for its n, and then one of these numbers for its L, but it has to be a number that corresponds and obeys the rules with the n, and it'll have one of these numbers associated with it. It'll have one of these and one of these.
How do you get a -1?
Hold on. So let's just go through this. I think I'll answer all your questions once we go through this. So let's pick an electron, any electron. So I go up here and I've got an atom and I pick an electron. I'm going to pick beryllium. Beryllium is my atom, and I'm going to put an electron around it. And this electron is going to be in some state of energy. Let's say that in beryllium, where beryllium Z equals 4, that means there's 4 protons in beryllium. Because it says right here on the periodic table.
So that's the common number for
That's right. That tells you how many protons are included. So now there's an electron going floating around out there around beryllium, just one all by itself, and it has some kind of energy associated with it. If you measured the energy of electrons going around beryllium, you would discover that they always had certain energies. That if you measured it again and again and again and again, you would end up with a table of energies where it was this energy 50 times, and this energy 20 times, and this energy 23 times, and then you'd have maybe end up with a couple of dozen energies, but nothing in between those energies. It would always come back to those certain number of energies that you've measured. And one of those energies might be associated with the principal quantum n equals 1. So let's say that one of my electrons has an energy level that is associated with n equals 1. If I plug z equals 4 and n equals 1 into here, I would calculate that energy for n equals 1. That would tell me how much energy it had. And it would correlate with that. If n equals 1, the rule says that L can equal 0, 1, 2, 3, 4, all the way up to n minus 1. So n equals 1, what's n minus 1? 0. N minus 1 is equal to 0, so L can only equal 0 to 0. So there's no angular momentum if n equals 1. If there's no angular momentum, because L equals 0, and this rule says it goes from negative L to positive L, well, L is 0, so what is m sub L going to equal? 0, because 0 to 0 is 0, right?
Alright, but how do you get to your negative?
You don't yet. Wait, we'll get there. Okay? So for n equals 1, you can have L equals 0, and you have to have m sub L equals 0. However, for the spin of the electron, you always have s equals 1/2. So this can have this one can have two different possibilities. If n equals 1, then L can be equal 0 and n sub L can equal 0. So that's a possible state. But there's a splitting here because S always equals 1/2. Crap. Hence, S always equals 1/2, and that means that n sub S can equal either 1/2 or negative 1/2. That means that there are two possible states. I have one state where n equals 1, L equals 0, n sub L equals 0, S equals 1/2, and n sub S equals negative or positive 1/2. Right, spin up. Or I can have this state, n equals 1, L equals 0, m sub L equals 0, S equals 1/2, and m sub S equals negative 1/2. Those are two different energy states. The only thing different was the spin up or the spin down of the electron. But those will have different, those will show up differently. They'll split in the spectrum. There'll be two lines, one associated with
It doesn't have one orbit.
They'll be in one orbital. This is your orbital. They'll have the same angular momentum. They'll have the same z component of their angular momentum, but their electron spin will be different. One will be up and one will be down.
And we only figure the outside spin wherever we're dealing with.
Yeah, so the spin,
We're only looking at the outer ring. Because the inner rings have to be fixed, correct?
yeah,
They can't
if
change.
we're doing,
They can change.
we're just looking at one electron. We don't care about what's going on with the other ones. And in fact, we've actually gotten rid of all the electrons. We're only looking, when we do this, we're only looking at one electron. So this is what this one electron could be. It could be this one, or it could be this one. There's two possible states. And since we never really look at just one beryllium atom, we usually look at a million of them because it's hard to look at just one, we will end up seeing about half and half. We'll see about half the ones that we look at will show up as this one state on the left with the spin up. The other ones will look at like the one on the right with the spin down. And so we'll see two energy states. Now let's do something a little more complicated. Okay, well, when we're studying atoms, what we're doing is we're exciting the atom. We're exciting the electrons in the atom using electricity or heat or something. And we're looking at the spectrum. And the spectrum will show up as a single line of light from the electrons that are going up and down between states, right? As those electrons go up and down between states, if we apply a magnetic field, we'll find that that single line will split into two lines if we're at the n equals 1 state. And we know which line is the n equals 1 state, so we'll see that it'll split into two lines and there'll only be two states, and these are the two states that they are. This is why there are only two, because we were at the n equals 1, and these are the only possible quantum numbers according to these rules. Okay? Now let's go over the rules again so that it makes a little more sense again. The rules state, and there's a place in here in the book where you can see the rules, right here. The rules state that if n equals 1, then L can equal 0 all the way up to n equals minus 1. Or sorry, L 0 all the way up to n minus 1. Well, what if n equals 1, what's n minus 1? What's 1 minus 1? 0, right?
So the n minus 1, so you're just taking the top number, subtracting 1.
That's right. And that
cannot go to a negative 1.
That's right. It can't go to a negative 1, so this number can only be 0 if n equals 1, right? Now, if n equals 2, if we're in the n equals 2 state, so in other words, if our electron has jumped up to a higher orbital, it has more options. The higher the orbital, the higher you are away, the further you are away from the atom, the more options you have for more energy levels as an electron. So if we jump up to n equals 2, then L can equal 0 or 1. So you have two different angular momentums it can be. If you're at n equals 3, how many different L's can you have? You can have 0, 1, or 2, right? And then it just trickles down. If your L is equal to 2, then your M sub L can equal anything between negative 2 and positive 2, including 0. So M sub L can be anything between your negative L and your positive L, including 0. And those are all the possible quantum numbers for M sub L. That one make sense? Okay, so M sub L is just another number that represents an energy, and a part of the energy of this atom, or part of the characteristics of this electron in the atom. Okay, so if you're at an orbit that is associated with n equals 3, that's your orbit, you could think of it as, and you have an angular momentum that is associated somewhere between 0 and 2 because n equals 3, right? And that's your L number. Then there's another thing that's associated with your angular momentum that can be anywhere between whatever your L is. In this case, L was 2. Let's say L was 2. Then there's an M sub L number that can be anywhere from negative 2 to positive 2. Negative 2, 1, 0, 1, positive 2. So it can be any one of those numbers.
So if it's 3, it's from negative 3 to positive.
It would be from negative 3 to positive 3 if your L is. So this number is also going to calculate part of our energy. And it's weird because it's quantized. You know, you're so used to just having an equation that you can plug any number into that you want. But in quantum mechanics, we have equations. These are our equations, but we can only plug certain numbers in because that's what we see when we do the experiments. When they do the experiments, they notice that the energy levels only turned up with these certain values. And so they started to realize that the math that we used up to this point was not going to work. Right? Now the beauty of it is that, you know, calculus and algebra become a lot easier in this because you only have certain values you can use. You can't just come up with any old answer. There's only certain values, so you know where to look. You know, you don't have to solve any algebra equations when you're doing quantum mechanics. You don't have to do any calculus when you're doing quantum mechanics because calculus and algebra are both they're both mathematical structures that are dependent on continuous math, continuous numbers. You can use any number in the spectrum you want. But in quantized math, there are certain sets of numbers that you can use according to certain rules.
All right, so go to the spin.
So the spin is the easiest one. Because what we know about spin of an electron is that it only has, the spin of an electron is an angular momentum that is natural to electrons. Electrons have it all in life. We've never known an electron not to have it. And all electrons have a spin angular quantum number of 1/2. And you use this equation to calculate the spin. So the spin of every electron in the entire universe is this with 1/2 plugged into it. It's just the way it is. Okay? So all electrons have this property of spin associated with them. However, if you put them in a magnetic field, you notice that there's a slight difference in that spin. There's some electrons will go up in the magnetic field, some will go down in the magnetic field, and that's what this number tells us. So every single electron could have this quantum number associated with it, could either be -1/2 or +1/2, and that you plug into this number to calculate that other slight kind of variation in that angular density.
So you take the L equation and just take out the L and put a 1/2 in it?
Yeah, for the big S, yeah, and for that one, it's the same equation because it's still angular momentum. We should have calculated angular momentum, so it's the same equation. But in this case, the value is fixed. It's always 1/2 for
So it's a 1/2. Is it just 1/2? So it always
an
answers,
electron, it's always a 1/2.
so it always answers the same thing, right?
Yeah, it gives you the same number for every electron. Every electron in the entire universe has that same value. But every electron in the universe could also have another value associated with these. So in other words, you can think of it as all electrons are rotating at the same speed and have the same mass. You can think of it like this, even though this is not true. It's still, you can think of it this way. It's as if you had a bunch of spinning tops. So it's as if you had a bunch of spinning tops and they're all exactly the same mass and they're all exactly spinning at the same rate. You know? Which makes no sense. Why would all the electrons in the entire universe be spinning at the same rate? First of all, that doesn't make any sense. But they all have this intrinsic characteristic that behaves as if they were all spinning at the same rate. However, it's like some of them are spinning this way and some of them are spinning this way.
Roughly half.
Roughly half and half. In fact, it's exactly half.
So what numbers do you use for S? Just 1/2? Only?
Yeah, for little s, you always use 1/2. But for m sub s, you could have -1/2 or +1/2. It could be one of those. That would be the up or the down, or the clockwise or counterclockwise.
Basically, on every problem they ask for M sub s, you just put 1/2 or negative.
Yeah, for sure. So those are your two options for every electron. Now,
And there's no way to tell without sticking a magnetic field, so.
that's right.
Alright,
Now,
so
not all particles. Now, all particles have these characteristics as well. Not all particles exhibit them. For example, some particles do not have an intrinsic spin to them, but some do. But they're not all particles have spin 1/2. Not all of them have s equals 1/2. But electrons are always 1/2. Neutrons have a different one. I think they're just 3 halves.
I think my cat is an intrinsic spin like that.
Packer has an intrinsic spin with quantum mechanics. But I mean, why is this? Why are you confusing the heck out of it? Because this is what they saw when they did the experiments. It's not because they were trying to make it hard. They were trying to make it easy. They were looking at it and saying, well, if you're running around in circles on a track, you get this kind of angular momentum. So of course that's what electrons have. When they did the experiment, it didn't work. They're like, it doesn't work. It's not working. How do we fix this? And so they had to be extremely creative and say, well, since it only occurs at certain amounts, we have to create a new mathematical structure to create a new physics. And that's what they did. They created an entirely new physics that is based on only certain values are allowed to be plugged into the equations. This is like saying force equals mass times velocity. That's Newton's second law. That's like Newton coming along and saying force equals mass times velocity. Mass times acceleration. Force equals mass times acceleration, but you can only have masses of 1 kilogram, 5 kilograms, and 7 kilograms. Those are the only masses you're allowed. Sorry. No. Because that's all I ever see. I only see things that are 1 mass, 1 kilogram, 5 kilograms, 7 kilograms.
So on this
But
piece,
that's what they saw.
so on this piece of paper, I'm writing this down, trying to understand it, right?
Mm-hmm.
So my atomic number's 3. So your N can be 3, your L can be 0, 2. Your
Well, the atomic number does not determine n. N can be any of these numbers for any atom. This is just used to calculate your E at that particular moment. You just use Z in this equation.
I can remember trying to figure something out. It says, no, it's all wrong.
And it doesn't matter what your atom is over here, You can have any one of these ends.
Yeah,
Pick
but
one.
I thought we were only dealing with the outside ring.
Nope.
So the idea is, so there's nothing.
Your electron can be in that outside valence shell, but it can also be lower or higher. We can use these to calculate the energy level of any electron, of an electron in any level.
So a boring atom has an electron that just sits in one shell all the time, but now we're going to use electricity to make it pretend like there are more electrons.
Well, there is no such thing as a boring atom. All atoms have their electrons shifting around all the time.
I'm just trying to simplify.
I know.
I'm trying not to confuse that. You learned my chemistry class about valence shell and all that. Just ignore that right now.
Have you
That's
ta-
a dark corner.
Have you taken chemistry before, Scott?
Huh?
Have you taken chemistry before? Well, in chemistry, they teach this a little bit differently because they don't try to explain anything about how this came to be or why. They just said, this is the way it is. Memorize this and move on.
So it's more like you take 100 people and say, hey, got to run around the track. We're going to take the average of the first person and the average of the last person, and that records what most of the people are.
No. It's like 100 people running around a track. It's like 100 people running around a track, and you're the track coach, and you can't see them until they cross the finish line. Okay? But you're timing them, right? And you have 100 kids on your track team, and you notice that 25 of them all finished at exactly 6 minutes. And the next 25 all finish exactly at 6 minutes 15. And the next 20 all finish exactly at 6:28. And you're like, what the crap is going on? And the only way you can explain it is to say, well, this is the way track works. 50 people will always finish at 6 minutes. Because it happens this way every time you have a track meet. But you can't see where they're running. You only see when they cross the finish line.
Alright, so how do you figure out the velocity of it?
We don't figure out the velocity. It doesn't have a velocity.
It obviously does.
Why?
Well, according to Bohr mode, this is all kinetic energy.
Yeah, but Bohr was wrong.
Then why did you give me this question?
Because I do want you to use his theory to calculate what the electron would have, what velocity would have if Bohr was right. We want you to calculate these things so you can understand the difference between his theories and the theories that came after. So you're going to go ahead and use his theory. There is an equation in the Bohr theory section, which is section 30. There is an equation to calculate the velocity or the kinetic energy of the electrons. Because they don't show you the equation. What they do is they show you the equation for the radius, and then you can use that radius to calculate the velocity because it's going around in a circle. So that's what you do.
Scott, when you become a well-famous quantum physicist to prove Bohr right, you can come back and teach this class.
So yeah, that is something that we want you to do so that you can recognize that. I mean, one of the reasons that it was kind of ridiculous that these electrons are going around is that they would have to be going extremely fast, and they would definitely not be able to maintain that orbit. They'd be going so fast that they would decay and collapse in the
They always
nucleus.
had to be accelerating in some.
No, the problem is that they would be always accelerating. They don't want them to be accelerating ever. Because anytime a charge accelerates, it loses energy.
Yeah,
And
but I thought it was always accelerating. There's a thing
That's
Yeah.
I know that Bohr was wrong.
yeah, that's why Bohr was wrong. Because if they were going around and around and always accelerating, then they would always be losing energy, which means their orbit would be getting smaller and smaller and smaller and eventually crash in the nucleus. And at this point of the universe, the entire universe would be one single point of nuclei and electrons.
Yeah, but whenever you accelerate, you can speed up or slow down.
We don't
It
have
doesn't matter if you speed up or slow down, you would still lose energy if you're a charge, because all charges lose energy when they speed up or slow down. So, with charges are peculiar in that no matter which way they accelerate,
So
speeding
even
up or
though
slow
you
down,
wrote
they
that
lose energy.
equation beside S, it's really just a positive half or a negative half.
This equation right here.
Yeah.
No, this is little s. This is big S. So this is the actual value of the angular momentum that the spin of the electron gives to the
So
electron.
it's either half, 1.5, 2.5.
So it's going to give you, then they take the square root and multiply h over 2 pi. And that'll give you the actual value of the angular momentum.
That will give you energy.
That'll, well, it'll give you momentum.
So the half is always related to what?
So the half is always used in this equation to calculate the angular momentum of the electron. Now, since it's always a half for an electron, you only have to calculate it once in your entire career and you're done.
So it's a half, just 0.5, plug it in.
Yep, plug it in and that'll tell you that tells you the angular momentum of
And
an
that's
electron.
big S always.
That's always big S for an electron. Not for a neutron, not for a proton, not for a muon,
Not an electron.
for an electron.
Okay.
Actually, I think muons also have. But anyway.
Alright, so S sub Z.
And then S sub Z tells you something about that angular momentum. It essentially kind of tells you that that angular momentum can be either pointing one direction or the opposite direction. It can
So it's
be,
either positive or negative.
yeah, so that one ends up being positive 1/2 or negative 1/2 plugged into this equation. So you get, essentially what you're going to get is going to get h over 4 pi or negative h over 4 pi when you plug that in.
Okay, 2 pi.
Well, because it's 1/2, it's going to be over 4 pi.
Okay.
Because m sub s is 1/2 or negative 1/2. So let's do an example and see if we can make sense of this a little bit better. Here they show all kinds of pictures that represent the mathematical constructs, or these are actually the solutions to these equations if you plug them into quantum mechanics and mathematics. You actually get shapes, you actually get these volumes that actually represent where the electrons are found, where electrons can kind of exist around the atom. And you can see here that n equals 1 is just a very simple sphere. N equals 2 is like a shell sphere with a little sphere inside of it. So n equals 2 has some more complexity to it. And this is n equals 2, L equals 0, m sub L equals 0. So this has no angular momentum yet. Once you start adding angular momentum, it starts splitting things up. It starts making things weird. It starts making a toroid, starts splitting things up into two things, another toroids and a split toroid. These are the things where things are orbiting. They actually have some angular momentum around the nucleus. And then, of course, the splitting in the S level takes each one of these and says, well, one electron here, one electron there, up, down, kind of things. So here is an example right here. We have, oh, here they no, it's to calculate the angle. I don't want to know the angle. That's lame. Never mind, I don't want to go into the angle that these make because that's just confusing. But let's look at.
Use a homework problem.
Is there a homework problem that does this? Sure there is. Hydrogen in the ground state, maximum width, okay. So here's a good example of this, of something for this. So in the next section, we're going to learn more about what these numbers 4s, 3p, 3s, 2p, 2s, 1s, all this stuff means. Suffice it to say, 1s right here is n equals 1. The 2s and 2p are n equals 2. These are n equals 3, and this is n equals 4. So suffice it to say that the first number is your n, okay? Does that make sense? So if n equals 1, what is L? The only option for L is 0. That means there's no angular momentum possible. And if we're going to fill up all, the different shells in this particular atom, then in the n equals 1 shell, we can only put 2 electrons in there because there's only 2 states. There's n equals 1, L equals 0, m sub L equals 0, and s equals 1/2, S equals 1, MS equals 1/2, and S equals -1/2. These are the only two states available when n equals 2. Oh, sorry, when n equals 1. So you can only have two electrons down there. One has to be spin up, one has to be spin down. Spin up is represented by this arrow. Spin down is represented by this arrow. So we click those two right there. And we're saying constructing a box arrow for the configuration of beryllium. Beryllium is right here. It goes all the way up to n equals 4, right? Now, and this is, yeah. Now, how many electrons total does beryllium have? You just count 1, 2, 3, 4. You know, it has electrons 4, right? So in the n equals 2 state, how many different energy levels are there? Possible. In the n equals 2 state, we have a possibility of quite a few states. And I'm going to use a little tree diagram to show this. We have n equals 1. We already did. For n equals 2, we have what for L? We have L equals 0 and L equals 1, right? For L equals 0, how many m sub L's do we have? Just m sub L equals 0, right? And for m sub L equals 0, how many S states do we have? Well, S equals 1/2. For S equals 1/2, how many m sub S states do we have? M sub S can equal 1/2, or m sub S can equal -1/2. Right? So right here, at the n equals 2 state here, how many states do we have? 2. This is a different state than this one, right? So this is a tree diagram where this state splits into 2. So this is 2 states possible here. If L equals 1, how many possible states can we have? Well, m sub L can equal 0 or 1, right? If m sub L equals, what's that?
-1?
Oh, sorry. -1, 0, and 1. There we go. M sub L can equal -1, 0, and 1. Thank you for that. And S is still going to equal 1/2, right? And so m sub S, in each one of these states, S can equal 1/2. So this you can go, this one can have S equals 1/2, this can have S equals 1/2, and they will all have S equals 1/2. And in each of these S equals 1/2 states, you can have a -1/2 for m sub S and a +1/2 for m sub S state. So each of these is going to have 2 states. 1, 2, 1, 2, 1, 2. So if L equals 1, how many states do we have? 6. Right? So in that second n equals 2 thing, you could fit in how many possible electrons could you fit in to all these states that are available? 8. 1, 2, 3, 4, 5, 6, 7, 8. And look here on the periodic table. How many electrons can you fit into the n equals 2 row? 8. If you're neon, you have all 8 of them filled up. Normally. That's how neon just exists normally. It has all 8 of those in the n equals 2, and it has the 2 in the n equals 1 state also filled. Right? And these are the ground state, the normal states of these things. If you're beryllium, however, how many of them have you filled up? If you're beryllium, you've only filled up 2 of these possible states of electrons. So for beryllium, what do we click into the 2's? Up and down in the 2s state. Now I said that the first number in these represents the n. Can you guess what the S and the P's stand for? Angular momentum. Right. So the S, what is the S going to represent? L equals what? Represents L equals 0. What does L equal 1? It's a P, right? So the P's are L equals 1. Why do we use S's and P's instead of L's? Because it was the Germans that were doing this. The Germans figured this all out, and they used the S and P to them are actually the first letters of words in German that have to do with how they named these states, and that just kind of carried over. So we can blame the Germans. It's the Germans' fault. So this would be the electron configuration in the ground state of beryllium, where you have 2 electrons filling up n equals 1, L equals 0, and n equals 2, L equals 0. Now you could jump some of these electrons up to a higher state if you didn't want to be in the ground state. These electrons could jump up to this state if you want to. Or you could jump them up to other states. But in its ground state, in its normal configuration, this is what it's like. It's filled with 4 electrons. Does that make any sense at all, Scott? Does it make any sense that this represents the n equals 1 state?
Yeah, the up and down spin.
And this equals the n equals 2 state? With L equals 0?
Well, it's okay for L equals 0, right?
Right.
There's 0, 1.
Right, so those are possible states, but beryllium doesn't have any more electrons to put in those states. Those states are there, they're available for the electrons to go into. But
So how do you, so, whatever.
so remember when you asked me about that Z? Z tells you how many available electrons you have in this problem.
The atomic number.
Yeah, Z tells you you have 4 protons in your nucleus, which means you have 4 available electrons going around it, right? And so if you have 4 available electrons, you will start filling from the bottom up. N equals 1 is the bottom state. So n equals 1 is this 1 state here, and you put in 2 electrons there. So 2 of your 4 electrons are now gone. And it's an L equals 0 state, because if n equals 1, you only get L equals 0. And so you only get these 2 states. So you fill up those 2 states, one is spin up, one is spin down. And then you go to n equals 2. Well, in n equals 2, the first lowest state is L equals 0 again. And it only has 2 states, m equals 1/2 and -1/2 for m sub s. So spin up, spin down again. And if you can fill up those states and you still have extra electrons, you'll start filling these states, which are these 6 states in the L equals 1. The little L equals 1 states.
Does that mean you just click them all?
You just click them if you have available electrons, but since we only had 4 electrons and we've used them all already, we're done.
So this right here says how many states, but that ain't the end.
This problem here shows you all the states all the way up to n equals 4 and L equals 0, but we're only going to fill them until we're out of electrons. Since we only have 4 electrons, we just fill the bottom 4 and we're done. Because once you have electrons, you're not going to put any more electrons in there.
Okay.
Don't be too worried about understanding or not understanding this in great detail. If you decide to take a chemistry class, you'll learn it in a different way, which may make more sense to you, may not make more sense to you. They teach it very differently, like I said. I prefer this way personally, but and I can't even remember how they taught it now because to me it was just memorizing things and spitting it back at the teacher when they taught it. But here, we kind of we want to try to understand where it came from. So hopefully we can help with that. But do you know how to answer this question? How many valence electrons does magnesium have?
Well, you look at the atomic number, and that's how many of them.
Not quite. But you do, this is related to what we've just been talking about. Remember that each one of these levels here represents an n number, right?
Right.
Your valence electrons are in the last shell of your n number. So if we're magnesium is right here actually. You're in n equals 3 because you're in the 3rd row. And then however many electrons you have in that level tells you how many valence electrons you have. So magnesium has 1, 2 in that level because it's the second one in. And so it only has 2 valence electrons. So if you were, let's say we were phosphorus over here at 15 or oxygen over here at 8. Oxygen is in the second level here. You go 1, 2, 3, 4, 5, 6. It has 6 valence electrons in its valence shell.
And that's how many electrons it has in its outer ring.
That's right. The outer ring is represented by the row that it's in. The number of shells is represented by the number of the column that it's in. Right? And you don't count these columns in between until you get down to these levels. Okay, so in the periodic table, usually the big bold number is your atomic number of protons, number of electrons in the neutral atom. The symbol here, the letter, is the atomic symbol, they call it, I think, or something like that. The element symbol, they're calling it. And then here, of course, is the name of the element. And then down here, that is called the atomic mass, or the sometimes called the atomic weight. But it's technically the atomic mass. And that tells you if you had 6.0 times 10 to the 23rd of those atoms, that's how much it would weigh, how much mass it would have in grams, essentially.
So for that one, it'd be 8.
No, for this one, for oxygen, if you had 6 times 10 to the 23rd oxygen atoms, it would have a mass of 15.99 grams. That's how much mass oxygen has if you have 6.
You get the number 6 times 10.
It's called the Mole's constant.
It's a constant created by a chemist who was doing a bunch of studies, and it turns out that while he was studying while he was studying, he noticed this discrepancies between the number of electrons and the mass of these things. And so he started keeping track of it. And he decided to base everything on carbon. And so carbon, if you have 6.0 times 10 to the 23rd carbon atoms, you have exactly 12 grams. Is it 12, or is it carbon?
I thought you did hydrogen in 1 gram.
No, you based it on either carbon or oxygen. I can't remember which one. It might have been oxygen, but he based it on something that had an exact number, supposedly. And then he calculated how many atoms that would be, and he called it a mole. And it's jokingly referred to as the chemist's dozen. You know, kind of like a baker's dozen, but a lot bigger. So so if you have a mole of oxygen gas, for example, a mole of oxygen gas is like an armful. It's like if you put a big thing of gas, it would be about that. It's like 23 liters or something.
So does it equate to the number of atoms, or does it equate to the area, or
The number of moles?
the weight?
No, it equates to the mass of that number of atoms, of a mole of atoms.
So it's a number of atoms.
We don't use it.
It's a mass of a number of atoms. Right? The other thing that this number can be used for often is you can use it to figure out how many nucleons you have, or in other words, how many neutrons. So each proton has a mass of about 1, and each neutron has a mass of about 1. And if you have 8 protons and your mass is 16, then you know you have about 8 neutrons as well. So you notice with hydrogen, the hydrogen, the mass is about 1, and so it just has a proton usually. Sometimes there's a neutron in there, but very rarely. So it's mostly, hydrogen is mostly just a single proton. But if you look at helium, its mass is 4. So it has not just 2 protons, it also usually has 2 neutrons in it. And the more that you have, whenever you have more than 1 proton, you have to have neutrons as well. Otherwise, they won't stick together. So, anyway. Same kind of thing here. So here's where they talk about the subshell notation. So the rules go that you have the ones, the big numbers represent your n numbers, okay? The s's and the p's, and there can also be d's and f's, and you see them here. Those relate to your L numbers, so the s's are L equals 1, your p's are L equals 2, your d's are L equals 3. No, sorry. S's are L equals 0. And S's are L equals 0, not L equals 1. S's are L equals 0.
Your N number's 1, your L number's 0.
For this right here, yes. So S's are L equals 0, P's are L equals 1, D's are L equals 2. No. Yeah. D's are L equals 2, F's are L equals 3. Okay? And then this number here, this little 2 here, tells you how many electrons are in that state. Okay, so in this particular configuration, we have in the n equals 1, L equals 0 state, we have 2 electrons. In the n equals 2, L equals 0, we have 2 electrons. In the n equals 2, L equals 1 state, we have 6 electrons. In the n equals 3, L equals 0 state, we have 2 electrons. In the n equals 3, L equals 1 state, we have 3 electrons. And so we want to know, what is this, right? What is this atom that has these states? So we go up to our periodic table. N equals 1 has 2 electrons. Boom, boom. It's full. N equals 2 has 2 electrons. Boom, boom, that's full. N equals 2 has 6 electrons in the L equals 1 state. 1, 2, 3, 4, 5, 6 electrons here, right? That's the next one. Then N equals 3 is this next row. So that, this is the S. These are all the S subshells, by the way. So all the S's are here. All of your P's are over here. Your D's are here. And your F's are down here. In case you're wondering. So S's can only fill up with 2. You can get up to 6 in your P's. In your D's, you can get up to 10, and in your F's, you can have, I don't know. But anyway, so we were at 2P, 6, so we got our P, our N, so N equals 3 is filled as well, so N equals 3, S2, so S squared, but that's 2 in the S. And then we have 3P, so that's third row. P means that we're in our L equals 1 state, which is over here. This is L equals 1. And we have 3 electrons in it. 1, 2, 3. Phosphorus. So really all you have to do is look at the highest number as long as these other ones are all filled up. If, you could also just add up the number of electrons and get the atomic number and you're done. Right?
Take the exponents.
Don't make it too easy. Come on.
Take the exponents, add them up, and look at the atomic number.
So this one is phosphorus A right there. So what Packer is saying is you could just take all these numbers up here in the exponents, add them all up and match it with a number on the periodic table, and that will also give you the answer. It'll be easier that way, but we want you to do it the hard way. Come on. The reason that we use this notation in physics and chemistry is because this can actually show you whether or not electrons have jumped up to higher levels. So you could have 1s2, 2s1, and 3s1. So you've jumped an electron up to the n equals 3 state. So there's an electron out of place, in other words. And you'd still add up the electrons in the exponents to find out what your element is, as long as it's not a ion. And then you could figure out from there, but then you could also figure out where the electrons are inside the atom. So if, for example, in my
So if the electron are moving, you couldn't do the exponent to count and get it right.
you could still do the exponent thing, but from this you can also tell where the electrons are at. So let me give you an example. For hydrogen in its ground state, when it's in its ground state, the electron is in the lowest level, which means the hydrogen has it's in 1s1 state is what it's in. N equals 1, L equals 0, there's 1 electron. Okay? However, hydrogen can also be in 2p2. Sorry, 2p1. It can't be in 2 because it only has 1 electron. So hydrogen can also be in 2p1. So if it looks like this, hydrogen 2p1, then we know that electron has jumped up from this n equals 1 level to this n equals 2 level, and it's in the p state up here. It's in the L equals 1 state, because it's in P, and there's 1 electron. So in my experiment, in the experiment that I did as a master's degree student, we had calcium, and we had jumped up electrons up into a higher state. We were going from one level to another level. So in my paper that I wrote, it actually shows this configuration in the title. It says the electron went from this state to this state with the S's and the P's and the D's and all these things. And we use a slightly different notation, so I won't show you the actual title because it's atomic physics. It was the same idea where we're using these letters and these numbers so that people can look at it and know exactly where the electrons went to and where they came from when we were doing our experiment. Let's look at some other ones here really quick. How come it won't let me move? Leave page.
It's a minute.
I think the computer's just busted. I think our internet is broken.
I think you have 6,000 times over.
Here we go. Okay, so we talked about valence electrons. So here's another way that we do this electron configuration. Sometimes we put an element in brackets like this, and what that means is that it has all the electrons all the way up to this point. So it has every electron before argon. So this is argon, and then 3D.
This is a whole other class. This should be like a chapter of itself.
So,
We still have another section.
so the 3D level is actually this one. This is actually n equals 3. When we get down here, n actually drops down a number. So this is the n equals 3 state. So 3d4 would be 1, 2, 3, 4 electrons in here. For titanium, which is what I want, it's 3d2. Oh no, is that right? No. This is still 4. So argon 4s2 for d2 is where titanium is. So it's the last one, I think. Yeah. 4s2 for d2.
I think the atomic number of
Oh, I was wrong. I think it actually was this one. Yeah. So actually, I was right before. So once you get down to the level where you have the D's actually jump back a number in quantum numbers. So this is 3D, and then 4D, and then 5D here, 6D. Actually, this is this becomes the F level. But anyway. But they do show that in that section of the book. And groups. So the groups are the columns. These columns here, and they show you the columns all have a number associated with them. Show you in the book there. Let's see, where is it?
That's vertically. For that question, number 12, it's vertically.
Yep. And then the periods are the rows. Let's see what else here. Heisenberg uncertainty. So the Pauli exclusion principle. This idea that electrons can either be 1/2 or -1/2, and that one has to be spin up and one has to be spin down if they're going to be together in an atom. That's the Pauli exclusion principle. And it essentially says that all electrons, any electron in a state, electrons in a state have to have their own set of quantum numbers. You can't have two electrons that have the same spin up that are in the same state, or spin down in the same state.
Yeah, I'm trying to figure this one out, and what the usually.
This problem right here.
Yeah, it said that if they either spin up or spin down, right?
Yep.
But whenever I read through them, I don't see one that really.
It says right here, each electron within an atom will have its own unique set of 4 quantum numbers.
And that means it spins up or spins down.
Yep. So that essentially means that it has, each one of them has a different N, L, M sub L, and M sub S. Every electron has a different M, L, M sub L, M sub L, and M sub S.
And then
So it's within an M. Yeah. Within any given atom. Right there. And then here's just a question where they ask what numbers are possible, where the first number is your N number, your second number is your L number, third number is your M sub L, and your last one is your M sub S. Right? Which set of these numbers could happen, could exist?
How long except for the 3, 3?
Yeah, I would agree.
well, there's not.
Yep. So more than one of these is possible. Right? This one is going back to the beginning of the chapter where we talked about the energy level differences and calculating the wavelengths. That's in the Bohr section. You remember that? If you go back to here, Bohr's theory.
Yeah, because Bohr is where the protons meet, right? Photons.
Photons, yeah. So you're calculating the wavelength of the photons right here. That's this equation right here. So in Bohr's theory, there's still only one quantum number, right? When Bohr was there, he still thought it was just the n quantum number was the only thing. But as they studied more and more Bohr's theory, they discovered that there was more to these energy levels. There was more structure to the energy levels. And they had to develop a much more complex quantum mechanics.
I thought quantizing everything would make it simpler.
It does. It really does. However, it's difficult for us to wrap our minds around this. In the math department at universities, they have entire classes just to teach students how to wrap their head around this idea of not having a continuous mathematical, continuous number or continuous domain to work with. You know, when you think of the domain of a function, we always think, well, everything greater than x. Everything in the entire universe except for x equals 1, because that will turn this into infinity. But in the quantum world, the domain of a function, the domain of our energy function, depends on the domain of the previous energy function. Right? The domain of the L function, the domain of our quantum angular momentum, depends on what domain we're in the principal quantum number. The domains, the things that we can plug into our functions, depend on the situation. And they are definitely quantized, and sometimes they're finite. Sometimes there is just 1 or 2 numbers you can plug in, like with S and M sub S.
Like this one right here, I spent some time, like 45 minutes on this question trying to figure this out.
Okay? So how do we explain the distinct lines that appear in the atomic spectrum? All the atoms that else can only produce the same color as light. Well, that's not true because every single atom is different, right? So that's not true.
They all have a separate amount of energy that they can be.
Certain wavelengths are produced due to specific electron jumps taking place in the atom.
True.
That is true. Any atom with the same number of energy levels will produce the same distinct lines.
Wrong.
Wrong. Because every atom has an infinite number of energy levels. So that's not happening. The distinct lines correlate to the distinct number of electrons in the atom. Not true. Because the hydrogen atom can have 1 electron, but so can uranium. Uranium can have 1 electron if we strip all the other electrons off, and it's going to have a very different spectrum still, right? So the only one that's true is the specific jumping of the electrons. The electrons only go back and forth between certain energy levels, and they never even go in between those energy levels. That's the weird thing, is that they never jump. They literally take a quantum jump, a quantum leap. They never travel between the two, but they go from one to the other. It's like going to Kearney without ever going through Kozad. You know, I'm here and then I'm in Carney, and there's no time between the two things. So technically, this also violates what other principle we've learned?
Newton's mechanics, right?
No, Einstein's. Because if you're in one place and then another place, that can't happen.
Can't be in two places.
That's faster than the speed of light. And so they took care of that by saying they don't actually exist in any kind of place, that these energy levels do not correspond to places in the atom. That's why they said that, because if they did, then it would be jumping from Kearney to North Platte without ever traveling in between in an instant, and it would be traveling faster than the speed of light, and electrons can't travel faster than the speed of light. So they just say that we don't know about where they are, we just know that they have this energy, and then they have this other energy. We don't know why, we just know that it happens, right? That's the whole playing the pinball machine with the black blanket over the top. We just can't see it, so we can't assume it. Because if we assume that it's correct, we're breaking every law in the book, right? And this was another brilliant thing that they did, is they were able, like Einstein was able to see past the idea of space and time being fixed, and he saw, well, maybe it bends, you know? He was able to see past that. The people that developed this theory were able to see past the fact that they couldn't explain what was happening, but they just knew what wasn't happening. You know? They were able to accept that they didn't know what happened, but they knew what the results were. And they accepted that, and they said, we don't care if it doesn't travel. We don't care if electrons don't, get in a car and go from Kearney to North Platte. We just know that they do it, and they don't ever go through COSAD, and we don't care. We just know that they don't. And we're going to be okay with that, and we're going to just work that right into our math.
All right, so for the second part of that,
this part here. What does each element produce? Why does each element produce a unique atomic spectrum? So
we have the energy that they put off because of the number of electrons.
okay, so each element has a unique electron arrangement that produces different wavelengths of light. That's a decent way of explaining it. Let's look at some other ones. There's nothing wrong with that, except that philosophically speaking, it's not technically an electron arrangement, it's an energy level arrangement.
Right. It's the
Each electron element has a different number of electron energy elevels, which produce different wavelengths of light. I'm not sure what an elevol is, but I'm pretty sure that's probably close to being true, as long as we rearrange some letters, right? Each element has a different number of neutrons, which produces different wavelengths of light. So the neutrons, the neutrons are not the thing here that are producing anything. The neutrons are somewhat responsible for how the energy levels are created, or where they are, but they don't actually create any light, right? Each element does not produce a unique spectrum. All elements produce the same spectrum. Well, we know that's wrong. So it's either 1 or 2, and I would say 2 is the better answer, because the electrons are not the thing that are configured. What's
I
that?
was leaning towards the first one
They're both wrong.
because each element
They're both wrong.
has a different number of energy.
I think this one's right. Let's see. So it doesn't like that. Let's try this one. That one's right. The first one was right. But I actually prefer the second one because, oh no, the second one says a different number of electrons.
That's
That's the thing that's wrong about the second one.
They got an infinite number of energy.
Yeah. So if the second one said it has a different arrangement of electron energy levels, that would be more correct than the first one. But the first one is more correct because it says arrangement. Yeah. And the second one says elevels instead of levels. You should have known it was wrong because it said elevels instead of levels.
They are physicists. They're not physicists.
We physicists ain't no good at English. Oh, today is Tuesday. Oh, good. That means I don't have to teach anything else today. I'm tired. So this is actually how they determine what stars are made of and what's out there in the universe. Is they actually and they look at a star through a telescope, and then they split the star's light up into the spectrum. And they don't see like we see with the atomic spectrum by looking at atomic lamps. They don't see individual lines. What they see is a rainbow, but in that rainbow there are missing lines. There are like little dark lines in it. Why would that be the case?
Because there are certain elements that they just don't have.
Not exactly, it's
Or they
close.
cancel out.
But it's kind of like that. What's going on is the center of a star, if you could just look at the center of a star, you would see a beautiful rainbow with nothing missing. But on the outside of the star, on the outside surface of the star, there are elements there. And they block the same amount of light that they would normally give off. So if you put an element in between a white light and the observer, they'll observe the reverse spectrum, because the element will block those certain lights, and it'll absorb those lights instead of emit those lights. So in other words, the white light is exciting those things in the atom, but the light is absorbed instead of transmitted. That's something we talked about in the last chapter, but we review here a little bit. So what kind of light is represented? What kind of light represents really big jumps?
High frequency.
High frequency, which is
Low wavelength.
small wavelength, right? So,
Violet.
so X-rays and ultraviolet, those are big jumps, right? Whereas infrared is a really small jump. And radio waves are even smaller jumps.
Go back to
Hold on a second. Okay, 19.
the first one.
Okay, so what comes out? Photons, light, electromagnetic radiation, all the same thing, right? It's not heat that comes out. A heat wave is actually a movement of material, air or water or something.
Right.
And it's not nuclear radiation. We haven't learned about that yet.
Right.
So, and then the light produced by a neon light or firework results from electrons that are doing what? If light is coming out of a neon light and light is coming out of something,
Yeah, they're jumping from higher to lower.
that's right. They got to be going from higher to lower. So they're that are doing what? Jumping not too high, they're not leaving the atom. It's not being ionized necessarily, but returning to the ground state. So going down. Okay, so tomorrow we will do, we could do, I actually don't want to do a lab in this. This is,
Good, I don't want to either.
the lab for this is really quite cool if you do it right, but it takes a long time to do it right. And it's better for if you're really going into physics to do it right, because then you're really interested in all the, like if you're not going into physics, you're just going into something related, it can be really boring because there's a lot of nitty gritty tuning an instrument kind of stuff going on. So I've never really done it here at this school. But if we skip our lab until we do nuclear physics next week, that's more fun.
Is that what we're going to irradiate, Scott?
Yeah,
Not even decide, too small.
we're just gonna make something radioactive. Okay, so we'll do that next week, and so tomorrow what we'll do is we'll cover we'll start chapter 31, which will be our
Are you gonna
radioactivity and
open- are you
nuclear
gonna
physics.
open this up
So
till
we'll watch
Friday?
our video tomorrow. What?
Are you gonna open this up till Friday?
Is it closed?
No, it's gonna close in 12 hours. I'm not gonna have
So 30. Oh, 30. You really need till, you don't need till Friday. You can get this done tomorrow.
I gotta wait work tomorrow.
Thursday and Friday, of course, we're going to be gone, so it doesn't make any sense to have. Well, we're going to do 31 tomorrow, so you can do chapter 31 sometime this weekend, right?
That's his way of saying he cares about it.
And we'll be back on Tuesday, so Wednesday we can have chapter 32 due, and then Thursday chapter
Oh, you didn't do it?
33 can be done due.
I'm not gonna be here on Tuesday.
Yeah, we'll be here Tuesday.
We'll just be gone Thursday, Friday.
Thursday, Friday this week. It's going to get easier next chapter, I promise. Scott hates me. He's like, it's not easier, it's just different hard.
I'm just ready for this class to be over.
You gotta admit the calculations have been way easier. They're just not, I mean, maybe wrapping your head around this stuff is a little bit weird, but the calculations are easy. There's like no calculation. Oh man. Anyway.
I know where he lives.
Oh.
You can stop recording now.
Yes, I can. People don't want to hear me yawn.